Good morning, all of you. Today we welcome all of you to a seminar on eclipse. Actually, this year we have a annular solar eclipse visible in certain part of India, and on certain other parts we will have a partial solar eclipse. So we will show you a presentation. Actually, two of us, myself, Jayan Ganguly, who is a technical officer in Regional Science Center and Planetarium. I will be showing you about the science and the total phenomena of eclipse, and try to give some animations and also that the phenomena gets clearer to you. And then this year actually there is a particular very peculiar aspect of this particular eclipse, which will be spoken by Sri Manas Bagchi, who is the curator and project coordinator of this Regional Science Center at Planetarium Calicut. So again, so we start the presentation, and I hope all of you will enjoy the presentation. So let us start. So today we will be speaking on eclipse, and on June 21st we will have a annular solar eclipse. So it will actually start from say Congo in Africa, and then it will come through Pakistan, and then it will to the Indian border from Rajasthan, and it will go through actually Uttarakhand, and then Haryana, Uttarakhand, and then it will move on outside of the India. So in this particular way, in those aspects, whichever cities I have said you, that there actually we will have the annularity, and people can experience annular solar eclipse. But for the other part of the country, like in Calicut or in Calcutta or other part of the country, we will be experiencing a partial solar eclipse. Now today in this particular presentation, we will be trying to understand that what actually makes the situation so that from some locations we see an eclipse as a partial eclipse, and on some other locations we see it as a actually annular eclipse, or in certain cases when total eclipses are visible, what makes certain places to be in the path of the totality, and in other places as a partial eclipse, and some places actually eclipses are not seen at all. So we will have a holistic view of the full phenomena as such, and let us go through the thing. So this is a picture of actually what is called an annular solar eclipse. We had it on December 26, 2019, and we all actually from in Calicut in Regional Science Center, we had made a very mega event out of it, and a lot of people, thousands of people came here, and we have projected it on a big screen, and it was really a big gala, and we actually enjoyed the full phenomena as such. So let us see what are the circumstances, because details of this year's annular solar eclipse, that is on June 21st, 2020, which is also the summer solstice, that is we have the longest day during that particular day. Every year actually we have on June 21st the longest day, summer solstice. So there actually the sun reaches its maximum declination. So from on June 21st, what are the circumstances from Calicut? Let us see that the eclipses, the duration of the eclipse will be around 3 hours 12 minutes and 15 seconds, and it will start at 10:08 morning, 10:08:15 seconds. That is morning 10 hours 08 minutes 15 seconds, and it will reach its maximum at 11 hours 38 minutes 32 seconds. So 36% of the actually the sun will be blocked by the moon, and then it will end, the partial solar eclipse will end at around 13 hours 20 minutes 30 seconds. So we will be trying to web stream the eclipse from our center, and I hope that this eclipse also, if weather permits, of course, because this is a rainy season in Calicut, and in certain part of in other parts of India also it is a monsoon time, but we hope that at least in the path of totality, in the path of annularity, people do experience, because annularity is also for a very short duration this year, only around a few seconds, or maximum of around some few seconds only people will get the annularity. So it is a very short duration of annularity. So actually if it is cloud free, then people can enjoy from there, but on other parts we will be enjoying partial solar eclipse. So let us try to understand, because regarding this particular solar eclipse, the second speaker will be speaking and throwing much light on that particular aspect. What is the peculiarity of this eclipse, and how this particular eclipse distinguishes itself from other eclipses? So that we will be seeing in the second talk, second presentation. So let me actually go through the phenomena of eclipse as such, how it is. So let us start with eclipse geometry. So I will be showing you an animation seeing actually what makes an eclipse. So let us see the before we see the animation, I will be showing you which is eclipse and all these eclipses, either Earth's shadow fall on moon during a lunar eclipse, or and the situation will be somewhat different from if you are standing in a region which is illuminated by sunlight. So actually our shadow game of the eclipses are also of some sort of like this. Instead of clouds, we will have Earth or the moon taking its role. So let us see actually how shadow games of nature works. So before that, before we go into the animation aspect of it, let me give you a schematic sketch of actually what is the phenomena of eclipse, how it looks like. So geometrical interpretation of our eclipse phenomena. You see that in this particular slide, you have a sun here, and you have the Earth, and you have the moon moving around the Earth in a orbit. So here we have taken it for our consideration. We have idealized it as a circular orbit, but we know that it is not perfect circular orbit. It is a bit elliptical orbit, though the eccentricity is not very high. So you can see that as the moon is passing, it spends more time here and it spends less time here. And when it is here, actually it is in between sun and the Earth. So actually what happens is that moon shadow falls on Earth, and we actually experience a solar eclipse. And when it is in this region, what happens is that Earth shadow falls on moon, and we experience a lunar eclipse. Now you can understand from here actually the length of the shadow depends on actually how far is the sun, means Earth from the sun. So as our Earth is moving in its orbit, our Earth's orbit is actually an oblate. It is an elliptical shaped orbit. So and sun is actually residing, sun is placed in one of the foci of this particular orbit. So what happens is that during certain time of its orbital motion, revolution, at certain instances what happens is that the Earth is at a position which makes it nearer to the sun, nearest to the sun. So we call it as a perihelion. And in the certain other positions, actually what happens is that it is in furthest away from the sun. We call it aphelion. So the distance between the sun and the because the distance between the sun and the Earth varies, and this makes actually the angular diameter of the sun as visible from Earth also vary. So under certain condition, the sun's angular diameter will be bigger, and under certain other condition it will be smaller. So we will come to it, and I will show you a comparison of all these things in future slides. And from this particular slide, actually you can very easy, by applying very simple geometry, we can calculate the length of the shadow. For example, EV is this is the vanishing point. If you take V, and we have EV and we have SV, and based on certain similar triangle formula, we can form this particular relation, and we can find out the length of the shadow. So one more thing about the eclipses is something like that. See, any shadow consists of two portions: a dark portion, which is called an umbral portion, and a semi-dark portion, which is called a penumbral portion. So whenever we are in the dark portion of the shadow, we experience total eclipse. For example, if we are where moon is giving a shadow, and we are in the umbral position of the moon shadow, we get a total solar eclipse. Or whenever we are in the umbral position of the actually the moon is in the umbral position of the shadow, we experience a total lunar eclipse. And you can see that this shadow cone here, actually it converges at this point C, and the if the Earth's position is here, for example in the position E1, E1 can vary between M and C at various distances. So based on this, actually the amount of time which is spent in the, or amount of belt which is spent, the annular belt or whatever it is, the belt or totality belt or the ecliptic belt varies. And here actually what happens is in the extended shadow in the Earth lies, we get an annular solar eclipse. So this diagram makes it very clear actually how actually in what, under what conditions we get I will be explaining you slightly better in certain other logics we will be putting up as we move on through the slides, so that you can understand that actually under what circumstances we get different types of eclipses. So with this background, and one more more thing is that people say about that how many eclipses are possible in a particular year. So whether there is a minimum number of eclipse, whether there is a maximum number of eclipse, and these can be calculated because these celestial objects, as they keep on moving, once they start moving in an orbit, their time periods gets fixed, unless otherwise they have actually they have the orbital element changed due to some other phenomena, like they lose their angular momentum or something of the sort. Otherwise actually the period becomes fixed, and when everything is moving, everything has a somewhat fixed period, at least in a mean period. If you say it is a fixed average period, so you can go on calculating and predicting a lot of things, because orbit is fixed, velocity is fixed, and so velocity is at average velocity. I am not telling that it is moving at a constant velocity. Average velocity is fixed and the orbit is fixed, so we can find out, and we know the planes of the orbit. We will speak about the planes of the orbit. So we know the planes of the orbit, so we know the geometrical situation as such. So this helps us actually calculating at what time actually we will get an eclipse. So what are the conditions for an eclipse, if you know. So based on all these things, actually it has been calculated that in a per year actually it is possible to get minimum number of eclipse every year should be 2. It is not required that both the eclipse will be visible everywhere. At certain part of the globe, somewhere in the world, actually we will have an eclipse, but minimum number of eclipse in a year possible is 2, and both should be solar. And otherwise the maximum number of eclipse which is possible, we can't have 10 eclipse, 15 eclipse, or any number of eclipse we want, because our duration of the year is fixed and all other parameters are somewhat fixed. So based on that, actually the maximum number of eclipse which are possible is 7. So under that 7 category, the maximum number of eclipse, there are 2 particular options that also can be calculated and shown, demonstrated. Actually either we can have a 5 solar eclipse and 2 lunar eclipse, and 4 solar eclipse and 3 lunar eclipse. So you are observing from here actually that number of solar eclipse is more than the lunar eclipse, and that again can be actually understood from this particular drawing. You see that we have a larger window for a solar eclipse to occur compared to the lunar eclipse, which has a shorter window. So based on with this background, actually let us see the geometry, because animation of the geometry. This particular plane in which Earth is moving around the Sun, it's called the ecliptic plane, and when the Earth is nearer to the Sun, it is called perihelion, and further to the Sun, it is called aphelion. Now Moon is moving around Earth in another orbit, and when it is nearest to the Earth, it's called perigee, and when it's furthest, it is called apogee. And further, the plane of the orbital plane of the Moon and the orbital plane, our ecliptic plane, are inclined at an angle of 5.5 degrees, and it, actually this makes there are certain circumstances. And one more thing, you see, when there are 2 orbits, these 2 circles crosses at 2 points. These are called the nodes. So the condition of an eclipse to occur is that it should be in the same line of sight, because for example for a solar eclipse to occur, we should have Moon in between Earth and the Sun. So that is one condition. And one more thing is that the Moon should be at one of the nodes. But otherwise what happens is that since these two are at different planes, every time whenever the Moon comes in between Sun and the Earth, we don't experience an eclipse, because either it will be above the ecliptic plane or below the ecliptic plane. So that is quite important. And similarly on the other case also for the lunar eclipse. Now let us see, when do these eclipses occur? So as I was explaining you that these eclipses occur during, for example, solar eclipse occur when actually Moon comes in between Earth and the Sun, and so that the Sun's means when the Moon comes there, the shadow, we will show you a shadow cone, the shadow passes through the surface of the Earth, and if you happen to be in the umbral region of the shadow, you experience a total solar eclipse. And if you partially are in the umbral region, you experience a partial solar eclipse. If you are not in the umbral region, you don't experience an eclipse at all. Similarly, when actually the Moon's Earth shadow, as till Moon is between means Earth is between Moon and the Sun, the Earth shadow falls on Moon. The Earth shadow is falling on Moon. And as a side remark, I will say you that by observing this shadow, actually it was first concluded that Earth is spherical in fate. It is not flat as prehistoric people used to think. So this shadow, because only a spherical object can cast a circular shadow, so this shadow was there, and Earth's shadow falls on moon, and we get a lunar eclipse. And again, when the moon is fully inside from a particular location, when the moon is fully inside the umbral position, we get a total lunar eclipse. And when moon is only partially inside and passes by, then we get a partial lunar eclipse. So these are the conditions for an eclipse. So let us see the shadow. You see there, see, Earth is casting a shadow, moon is casting a shadow. Shadows are there every time in space, so there is nothing special for an eclipse to occur. Shadows are always present. But when the shadow incidentally passes or crosses the surface of the Earth, moon shadow crosses the surface of the Earth, we experience we experience a solar eclipse. And when Earth shadow falls on moon, we experience a lunar eclipse. So these are again actually demonstrated by these some graphics, and you can see these graphics are quite clear that you should the moon either the moon should be between Earth and the sun, and it should be in one of the node, so that will happen. And one more thing is, one more type of coincidence is somewhat like this, that the sun is actually 400 times further away and than the moon, and the size of the sun is also 400 times larger than the moon. So this makes actually the angular diameter under certain circumstances, angular diameter of moon to exactly match the angular diameter of the sun. So in such circumstances, actually what we get is a total lunar eclipse, total solar eclipse. So why it is total? Because the moon's sun's photosphere, that is the visible disk, that is the illuminating disk, is fully blocked by the moon, and so we can see the upper lunar other lunar atmospheric region like corona and the chromosphere. All these things are normally not visible to us because of the glare of the sun. So these angular diameters matches in during that state. And we can also calculate by using a small logic. We can calculate, that is, how many seconds are there in 1 degree. We can take it and we found make it converted into radians. Angular diameter small by 206265. This is that conversion factor is equal to linear diameter by distance. So if you can use that, we can calculate the angular diameter of various astronomical objects using this particular formula. Now, as I was telling you, that actually moon changes its angular diameter. Now, why does it changes? Because if you take a coin and if you try to see the coin at various distance from your eye by closing one eye, and if you just move the coin, its angular diameter change. Similarly, as the moon is moving around the Earth, what happens is that at certain position the moon is nearest to the Earth, we say that it is at a perigee position, and at the perigee position, since it is nearest to the Earth, its angular diameter becomes bigger. And after some time, actually in its as it goes on around its orbit, at a certain position, actually moon is furthest from the sun. In such a situation, actually angular diameter reduces and it becomes minimum actually, and that is the apogee position. So these positions are these two, and all the other angular diameters lie in between the perigee and apogee, and these two actually plays a major role in finding out means in ascertaining the duration of the eclipse. Because if for example if the moon's angular diameter is small and the sun's angular diameter is large, based on how large and how small it is, we will end up with the different types of eclipse. Like sometimes we will end up with an total eclipse, sometimes we will end up with an annular eclipse, so sometimes we will end up with an hybrid eclipse. So these situations changes based on the changing sizes and changing distances of the moon from the Earth. And so similarly, angular diameter of the sun also changes as observed from the Earth. So one more thing is that this moon's angular diameter changes. I will just make a passing comment as that this same change in angular diameter is observed sometimes when moon is rising above the horizon. So sometimes you will observe that as it is rising, moon appears very much bigger, and when it has gone up at a certain altitude, its angular size has come down. So what happens is that when it is rising, so you consider the moon, so each layer, if you segment the moon moon by a plane, by various parallel planes, each of these slices gets refracted, and they gets refracted by different amount, because that depends on the altitude of that particular segment from the horizon. And so they are refracted, and we get a somewhat a bigger image, more non-spherical, bigger oblique, slightly it is not a distorted image, but it is bigger. And further, when moon is rising, it is seen in our perception in comparison with the other houses and other trees which are on the horizon, so it appears bigger. And again, when it has risen to a particular altitude, we see that the angular size change. So that is because of a different reason, but this change of perigee and apogee and the angular size relation is based on a different reason. So that is one aspect we should keep in mind. And the second thing is that about sun, as the earth is moving around the sun, the earth's orbit is not a circular orbit, it's elliptical orbit. So at a certain situation of time, what happens is that earth is actually in a position where it is nearest to the sun. We call it is at a perihelion position. Since it is nearest to the sun appears bigger in angular size. Similarly, when earth is at a furthest distance, we say that earth is in a aphelion position, and it appears smaller in size. So as here actually it is shown that how the size has changed, because every year sun is as earth is moving in its orbit, it completes one orbit in one particular year, and at certain day of a particular year it will be in perihelion, and at certain other day it will be in aphelion. So this is very important. And one more thing is that, see, this year again you are seeing a circumstances where we are getting an annular eclipse. So again it is sun is bigger in size, so we will speak about it a bit more when we come to that particular slide. And certain situation when sun is bigger means actually earth is much nearer to the sun, so either it is nearest in the perihelion or it is actually approaching the perihelion. So how much near determines the how much bigger the angular diameter of the sun is, and that also determines actually how long that annular eclipse will occur. So we will speak about it when we come to that particular aspect. So let us have a comparative study, let a comparative view of the moon's closest and furthest and sun's closest and furthest, and how the angular diameter change. You see that for moon, since it is nearer to us, it is more appreciable, and then what is seen for the particular sun, though in both cases actually there is a change in angular diameter. So whatever we have spoke just now is actually shown in a pictorial form, and you see that the plane of the ecliptic plane, the orbital, that is the plane in which actually earth moves around the sun, and the orbital plane of the moon as it moves around the sun, they are inclined. And so for an eclipse to occur, actually two conditions has to be met. One is that we should have the eclipting object, like for a solar eclipse we should have the moon in between the earth and the sun, and for a lunar eclipse we should have earth in between the moon and the sun. So that is the first condition. And the second condition is that it should be in one of the node, because if it is in node, what happens is that since it is at the point of intersection of moon's orbit and the earth's orbit, so this point of intersection lies in the ecliptic plane where actually sun and earth is there, and that it is neither above nor below. Though if it is above and below, we will see there is a concept of eclipse season. We will come to it after some time, but then that is a small if there is small deviation still we get, but in this particular case this actually it is a fixed condition. These two conditions has to be met. And then we have different types of lunar eclipse. So let us, since we are actually discussing a general discussion on eclipses, so we will be discussing both the eclipses, lunar as well as solar. Let us see, you see this particular figure, we have the orbit of the earth, we have the sun here, we have the earth here, and the moon is moving in its orbit. And as I said you that there is a, for each for a particular for any shadow we have a umbra and and penumbral position. So umbra and penumbra or any shadow. So we have the umbra here, which is totally dark, and we have the penumbral region here. So as the moon is passing through it, sometimes it may happen that it lies in the penumbra, so we get a penumbral eclipse, which is not very appreciable because only 10% or 20% drop in intensity is there. So that doesn't make it a bit appreciable, though in calendar or somewhere we can see that there is an eclipse today, but we can't perceive it. But somehow if moon is partially within the umbral shadow, we see a partial eclipse, and if the moon is actually fully in the umbral shadow, we see total lunar eclipse. So that is the full geometry of it. Now as the eclipse progresses, it's very important and it's quite interesting to actually see an eclipse. It's quite a longer duration compared to a totality or something, but to perceive a lunar eclipse is quite safe. You don't have to have any optical aid, but you can just see in an open ground or in your terrace. If you go, you can see the eclipse starts. As it starts, actually you see that a portion of the moon gets shadowed. So here, as you see, that portion of the moon gets shadowed, and ultimately when the full moon is under shadow, what happens is that you see that suddenly the moon appears as a brownish red in color. So this is because actually the earth is blocked, earth's shadow is fully on the moon, but there are some light from various portions of the earth which gets refracted, and it falls on the surface of the moon, especially the redder, the longer wavelength falls on the surface of the moon, and how much it falls depends on the actually aerosol. So there is a scale called Langdon scale with which actually you can measure the amount of the color intensity and amount of aerosol in the earth's atmosphere from as it is observed from a particular region. So that makes it appears a brownish red or brown in color. And then after the totality, this only happens during the period of totality, total lunar eclipses, and after the lunar total phase is over, again actually it starts to actually come out of the eclipse, and it moves out and it becomes a full moon. So one thing is that a lunar eclipse occur during a full moon time, and a solar eclipse occur during a new moon time. And this is obvious because I am saying that whenever so for a condition for a solar eclipse to occur is that moon should be in between sun and earth. So when the moon is between sun and earth, the sunlight falls and illuminates. It always illuminates half of the moon. So half of the moon which is illuminated is fully out of our perception. So we only see the dark side of the moon, and that is what we call as a new moon. So new moon should be there. On the other hand, when actually we see on the other side, when earth is between the sun and the moon, so we see that when it is not in the straight line, when it's approaching the straight line, it is the sunlight is actually illuminating half of the lunar surface. So that half is fully visible to us. That is what we call as a full moon. So after that only we start the eclipses. So lunar eclipse only occurs on a full moon day, and the solar eclipse occurs on a new moon day. So that is quite interesting. And then there are some pictures of different eclipses which has occurred in different period of time. So this has occurred in the midnight, so it is even 7th, 8th. It has it progressed through the night, and it has crossed the midnight and gone to 8. So that is the reason eclipse on 7th or 8th 2017 is shown here. So let us now, we have seen about we have discussed about lunar eclipse. So let us discuss something about solar eclipse. So as I have said you that solar eclipse occurs when moon comes in between earth and the sun, and also the moon is or near it or on the node, that is the point of intersection of the lunar orbit and the earth's orbit around sun. In such circumstances, we have the moon shadow crossing a part of the crossing a section of the earth, and again the shadow will consist of umbral and penumbral region and all those things. And actually if you happen to be in the umbral region, you experience total solar eclipse. So sometimes under most favorable condition, it has been found out that the shadow cone, that is the cone, we have seen the shadow cone as we were seeing the animation, it actually, the shadow cone covers an area of 2,269 square kilometers on the surface of the earth, and the speed with which actually there are tourism for solar eclipse. People hire aeroplanes and chase the shadow, and the shadow speed actually moves, as as you move from latitude to latitude. At the equator it will have a speed, and at the poles it will have speed. So equator it is 1730 kilometers per hour, quite high, and the pole it is very far, very much higher, that is 8000 kilometers per hour. So the people actually take it as a challenge to always remain in the shadow by hiring a plane. So that is something costly, but even it's a natural phenomenon, and people do enjoy doing a lot of things of that sort. So that is the category of eclipse called total solar eclipse. So let us see video of the total solar eclipse. See, observe it. So you see that slowly, this is actually the eclipse as it is progressing. It is near totality. So this is vanishing. I have been to one such eclipse when it occurred in Patna, and when it vanishes, it becomes totally dark, and you see a magnificent ring surrounding that is actually we have the chromosphere first you see, and then you see the corona. So then after the thing, as the eclipse progresses, as the sunlight tries to come out from one of the lunar mountain and craters, you see the great diamond ring. And that is really spectacular. And wonderful thing is that everywhere it becomes dark. You are in actually broad daylight, and suddenly you see the light is fully cut off. Everywhere it becomes dark, and people actually, birds and all, fly away from each other. And this is really a wonderful experience for most of us. During a total solar eclipse, when totality is there, you can experience a lot of things. Once or twice actually I have been in the totality, and everything was going fine, and the sun's disk was actually getting covered by we were entering the lunar shadow. So we were seeing that the disk of the we were seeing with our spectacles and projected image. I will show you how actually people observe the eclipses. We were seeing that the sun's visible disk was getting blocked by the moon. And during just before the eclipse, we were seeing that there were some buildings, and there were some shadowy, wavy shadow which was observed actually on the walls of the building. And this actually happens because as the sunlight gets diminished, its intensity goes down, and the rays of sunlight comes and passes through the leaves of the tree. They form these types of wavy lines, wavy patterns on the some horizontal or vertical plane surfaces, and these are called shadow bands. And also when it just approaches the eclipse, you see there's some bead-like phenomena, which is like a bead. The limb of the sun appears like pinkish color beads, as you are seeing in this particular picture. These are called Bele beads. And when the totality comes total, actually when we have the total eclipse, what happens is that we get fully blocked, and we see the corona. I will show you a picture of corona. It's a very beautiful picture. It's like an halo, and that actually this halo around this sun, the solar corona, that was adopted for our recent COVID virus, and since it is spikes of protein surrounding it, they have named it as a coronavirus. So that's just a side remark. But again, when the eclipse gets over, what happens is that the light ray starts coming out through the craters and valleys. A small beam of light just comes out, and then suddenly it appears like as the light comes out, and then the light fully unblocks. So at that point, when it just starts to comes out, it appears as a diamond ring. So that is a very beautiful phenomena, the diamond ring. And then normally you don't see actually the solar atmosphere. We see the photosphere, and we don't see inside the sun what is there because of the electron scattering and ionic scattering. You can't see because of the opacity of the surface of the sun. You don't see actually what is within the sun. We can only see up till photosphere, and under specialized instruments and all, we do observe the granulation and all of the sun. So that is one thing. But above the photosphere, there are atmosphere, like we have solar atmosphere, like we have chromosphere, we have transition zone, then we have the corona, and the solar winds and all. Everything is there. So this chromosphere and corona, these are the prominent regions, low density regions, but these are not seen during normal time because of the glare of the sun. So when the moon eclipses, when the moon blocks the total light, we do have a glimpse of the corona just before, and the totality starts. We do have a thing of the corona, and that is what you are seeing. You are seeing that there are certain regions where it is reddish or reddish pink in color, because these regions contain actually hydrogen atom, and when they since these atoms are excited and getting de-excited, these atoms, hydrogen atoms mostly, they radiate in visible range in the Balmer's part of the spectrum. So this Balmer spectral light, what is seen as the pink light or the red light, as you are seeing. So, and when the totality comes, you see the corona, and there are some pictures actually which shows the hydrodynamic magnetic lines as it is passing through the plasma and all other atmospheric thing as it is coming out. You see that good structural picture. There are some very good pictures, but in this picture it is not so prominent, but you see lot of things. It depends on the photograph with which you actually capture the corona, but otherwise also it's a very beautiful thing that everywhere it is dark and you see a black circle surrounded by a halo surrounding it. It's a very wonderful sight and people should observe that. And after it passes, we will see the normal partial solar eclipse, and there are this slide shows the various phases of that. So we have different types of solar eclipse. So as I said you that one more type of, we have spoken about partial solar eclipse, we have spoken about total solar eclipse. So now we speak about the annular solar eclipse. So when we are in the extended part of this, remember the picture which I have shown you, the line diagram. So after the umbral region it crisscross and comes out. When we are in the extended part, as you can see here, see the picture, this shadow is falling and it got extended and then it falls here. So in such situation actually what happens is that you get a annular solar eclipse. So annular solar eclipse, the condition is that the angular diameter of the sun and the angular diameter of the sun is much bigger, no, at least bigger than the angular diameter of the moon. So moon cannot block the total visible disk of the sun. So when it is totally inside, we still have a ring of fire type of thing surrounding, a ring of light surrounding the moon, and that is what is known as a annular solar eclipse. So that is what we are going to experience in our Rajasthan, in Haryana and in Uttarakhand area, Kurukshetra and all the Uttarakhand area. We are going to experience the annularity as we have experienced in Calicut on December 26, 2019. So we experienced something of this sort. So it was a very spectacular sight, and it is very rare actually to get certain things at the same place twice. So it's quite rare. So naturally we have partial eclipse. If you are on the partially within the umbral region and partially not within the umbral region, we get a partial eclipse. So these are the various phases of the partial eclipse. Sometimes see it comes, it blocks a certain point. For example, here it will block this time in Calicut it will block around 36%, 36 to 36.5% of the visible disk of the sun. That is called the magnitude of the eclipse. So how much blockage is there? So we have the different phases of the eclipse which is shown in this particular slide. Certain times it happens that actually we have an hybrid eclipse. Hybrid means at certain places we have a totality, at certain places we have actually the annularity. So these two happens together, and we have these two doesn't happen together, means in the same time at the various location. At some point it is seen as a totality, and some point it is seen as an higher annular, because based on the latitude difference and all those things. So we get hybrid eclipse in those during that time. So duration of the totality or duration of annularity, how it is. So as I told you that this all depends on the angular diameter. It's a game of shadows, a game of angular diameter. So when actually sun is bigger, moon is exactly matching the angular diameter of the sun, we get a totality. And when actually moon is in the say perigee position, that is moon is nearest to earth, and earth is in the aphelion position, that is sun is very small, comparatively smaller. So moon actually blocks much bigger portion, means beyond the solar diameter actually moon blocks. So moon actually the blockage remains quite considerable. It is somewhat like an opposite of annularity you can consider while explaining, that's all. So the totality of this duration of totality becomes larger in such circumstances. So that is where you get a longer duration of totality, say 7.5 minutes totality. Normally totality varies few minutes or few seconds or something. For example, this time's annularity is only half a second in some places, or a few seconds. So this 7.5 2.5 minutes you have a totality duration. So this is only possible under very favorable circumstances, under these two conditions. And when it just matches, we have the normal totality, and sometimes we have the annular eclipse, as we are having, that is the third phase, which is shown in the figure. So depending on actually all these parameters, we have different types of we have a pattern of eclipse. Why there is a pattern? Because as I told you, that when an object moves around another object in our sky or in the space, they get somewhat fixed parameters, like their orbital parameter, because mass is not changing once they start moving. Their speed remains at a particular distance, remains somewhat, means it changes as it varies. The speed will vary, but on average the speed, we get a magnitude of the speed. So based on all this, actually we find out that the from full moon to full moon, or from new moon to new moon, which is called a lunation, or the synodic month, is actually 29.5 days. So from there actually we get the concept of the month, the thing. So that is one aspect. And then these nodes actually, it travels on retrograde with respect to the Earth. So Earth's orbital plane, and it completes westward motion. It completes in around 18.6 years. So these two determine the solar pattern of eclipses of the sun and the moon. So we have, because these nodes, we have the nodes, and as I told you, that this moon need to be at one of the node or near one of the nodes. So this aspect, the nearness to the node, also can give rise to certain situations of an eclipse, and that gives rise to the concept of the eclipse season. So it has been found out by calculation, and also has been verified by observation, that actually when the full moon occurs within a time interval, within a temporal interval of 18.75 days on either side of the node, so we can experience an eclipse. So if it is 18.75 before that, 75 days before that, or after that, so we get a window of around 37.5 days, and it happens, this window happens at an interval of 173 days interval. So during these types of interval, it is getting aligned, we get an eclipse season. And whenever one eclipse occurs, another type of eclipse follows, and in certain circumstances we get 3 eclipses also in an eclipse season. So based on all these concepts, actually we can formulate another concept called eclipse year. So eclipse year takes actually sun and all the returns to respect to the node in 346 days. So in there, if for each there have been 176 days, we have seen that. So there are 2 eclipse seasons possible, and then we have either 3.5, or in certain calendar year we have 6, and I have said you that maximum number of eclipses is 7. So we have a type of eclipse year where we can find out different types of things. And one more interesting aspect is that based on the different type of month, that is, moon is on node and it again come back to the node. Moon is the aphelion, apogee or perigee, and again come back to the apogee or perigee. Or moon is with respect to the stars and again come back, the sidereal period or synodic period, that is full moon to full moon, new moon to new moon. So these are giving rise to different types of periods. So one thing we just see that people have calculated and find out, if you take the synodic period, which is 29.53, and if you multiply with a particular integer, that is 223, you get a certain number. Similarly, if you take the anomalistic month, that is 27.55, and you multiply with 239, you get somewhat same close, where integral part is close, same, only the fractional part varies. And similarly, draconic month, that is node to node, if you multiply 27.21 into 242, we get again the same number. So this number is somewhat constant, and this number is equivalent to 18 years, 11 days and 8 hours. So this is called a Saros. After the Saros, actually all the sun, moon and our earth are relatively in the same positions, and the eclipses recur, and all these eclipses, whatever we see, they belong to one or the other of the Saros cycle. So we have a pattern of Saros cycle shown here, and I think, and based on this series, actually all the eclipses, as we go on seeing it, they fall in some or the other of the Saros cycle. So sometimes the Saros cycle begins in one of the pole, and it ends at the other side, and it lasts. The Saros cycle is quite huge enough, and it lasts around 1226. It lasts between this and 1550 years, comprising of 69 to 87 eclipses. So these are quite interesting patterns. So these studies are also being taken up by astronomers. So with this, actually, I stop my presentation. I hope you have understood the phenomenon of eclipse, and I ask Manas sir to actually continue with his own version of the eclipse. Sir, can you take over now?
Thank you, Mr. Ganguly.
Yeah.
Well, welcome, and my hearty best wishes to our viewers. We thought that quite often, whenever some solar eclipse comes, we get into some kind of event and the mood of festivity. It is good that nowadays we come out, we actually want to see and observe what is happening, but at the same time, there is some catch in it. We found that while the festivity catches up, the real senses of logic doesn't really come to our consideration. We do not much subscribe to the ideas why this happens and what are the finer points that we need to observe. Now, we are thankful to Mr. Ganguly that he has given a very elaborate and detailed scientific explanation of different situations of solar eclipse, and he has also explained different kind of cycles. I would like to talk about certain specialties that we can relate to, a few in generally to the solar eclipses and a few which are specific and particular to this eclipse. Well, for that, allow me to just give me 1 minute. I load up my presentation and then I'll go into it. The title here we have given is "What's Special This Annular Eclipse or Partial Solar Eclipse." So we mix it up because on the path of so-called totality or annularity, we will see an annular eclipse this time. But from the other parts of our country, we can observe a partial solar eclipse this 21st June 2020. And there are certain things which are special. I would like to pose a question first. The real issue is that there are certain observations that we do not process. Even when we look at it, even when we find it, we do not really try to understand what is the meaning of it. So, yes, of course, the brilliant spectacle of total solar eclipse of or an annular solar eclipse is really enjoyable. But we request you that you be observant as well, and please look at certain issues. And the issues I'd like to cover is, there are 4 issues actually. The first one is, look at the eclipse path. Which way does the eclipse move? Why does it appear from the west? Then we look towards the speed of the shadow. How does this shadow move? Can we chase the shadow in an airplane? How easy it is? I'm sorry for the spelling mistake here. It's airplanes recorded here, but actually it's an airplane. Can we follow it and chase it with an airplane? We'll discuss how it is and how it would like to be. Then this is a solstice eclipse, and that is special. Why is it special? We will discuss. And we'll also look at the moon's path with respect to the sun, though it is not really connected to the actual path of the moon with respect to the sun. But when we see the eclipse, it's a complex mix of different sort of geometry and dynamics, and hence it appears differently. And this time it is very special in India. We would like to discuss all those issues. Let us first concentrate on the eclipse path. If you have an eclipse map, I mean the map of the path, total path that this particular eclipse will follow, please keep it handy. You will understand why we talk about it. I'll just go to it. Here you can see it. If you can follow my cursor there on the screen, you can see that we have placed the world map here, and then on this world map, this is the path of annularity. Okay, it starts here in Africa, in Congo in particular, and then it passes over different countries. We'll come to them later on. It of course goes through India and through China. It finally ends up in the Pacific Ocean. Now in Pacific Ocean there is a string of islands called Guam Island, and there it ends. But towards the end of the day, even though not on the total path of not on the path of annularity, but still you will have a partial solar eclipse at the northern Australia. At the tip of it, at the day end, you can see a little bit of it. Now this path of annularity, it extends, we can see it from Africa through Asia, and it goes on to the Pacific Ocean ultimately. It passes through different cities over this path of annularity. Later on we'll study that also, how it would look like over this complete path. We'll try to cover many different cities on this path, and we'll also cover a few cities of India where we will see the partial solar eclipse simulations, and there is something special in it. I tell you, you'll find it what it is. The issue is, we all know that the sun apparently goes from the east to west in our sky. It is always so because the earth moves from the west to east. So earth moves in space, and that is why sun, we see it going towards the other direction. The question is, why then the eclipse appears in the west first and then it traverses to the eastern direction? This is quite an intrigue, and we normally do not expect it to happen like that. Yes, on the daily stroll the sun goes from east to west in the sky. That's an apparent motion, of course, but the solar eclipse traverses the other way around. It is from west towards the east. What is the issue? Actually, the answer is quite simple, but it's not something that we are accustomed to thinking about. We do not normally attach it to our logic. We do not process the observation. What it is, the moon itself orbits around the earth from west to east. Yes, like many other satellites in our, almost all major satellites in our solar system, except in Triton, the biggest satellite of Neptune, it traverses the other way around, but moon traverses from the west to east. And in other words, what happens is, if you could rocket up high above the North Pole, the moon would trace out a counterclockwise circle. But Earth rotates about 30 times for a single lunar orbit. So it's not something we normally notice. We do not see the real motion of the moon. We can only see the apparent motion, and we see that the moon also is traversing in our sky from the east to west. But if you follow the moon daily, and even in a single night, you will find that moon is falling back slowly, little by little, towards the eastern direction. But when during the eclipse times, the sun is covered and there is an occlusion of sun by the moon, you can find out its a real motion. So what is the issue? The issue is, when we get to this condition, it is actually a competition between three different cases. Number one, sun's apparent motion towards the east. Number two, yes, the moon is moving towards sun towards the west, moon towards the east, and the earth's movement also towards the same direction. So what happens is there is a competition between the speed of the earth and the speed of the moon. It can be calculated. In fact, I would request you to visit to my blog where I give a detailed calculation of such things. The blog you can find out at consciousignorance.com, www.consciousignorance.com, where you can get the detailed account of all these. But yes, here let me tell you that the earth is moving towards the east quite fast, and the moon actually, since it is quite far off, even though it takes 30 days to cover almost 60 times the orbit of the diameter of the earth, the moon's orbital periphery is 60 times almost the diameter of the earth, and hence the moon is really moving faster in comparison to the earth. So when the shadow is cast on the earth's surface, even though the shadow and the earth are moving towards the same direction, actually speaking, the shadow is moving faster, and that is why we see that the shadow and the eclipse is moving from the west towards the east. But how fast it is? Can we chase it? Yes, we can. Can we ride a Concorde and actually follow the moon's path? Well, Mr. Ganguly has just briefly mentioned what the speed can be, but once again, let us have a little more detail. See, the shadow moves fast, I told you, but how fast? For the solar eclipse, what we see, we can find out that the Earth's surface is moving from west to east too, as I said. So it's a question of which does this faster. Although the Earth rotates once a day and the moon orbits only once a month, 28 times more slowly, the moon is also much farther away. So Earth's radius is about 6,371 kilometer. The distance to the moon is, to be easy, though it is actually 384,400 kilometers, but to make it easier, we can call it 400,000 kilometers, which is about 60 times farther away. This means that the moon has to complete a circle of radius 60 times Earth's radius in time, and that is 28 times Earth's rotation speed. So you can find out that the moon is moving quite fast. So the moon is moving much faster through this space than the Earth's surface is moving, about twice as fast. So the moon crosses the sun faster than Earth's surface moves. So what happens is the shadow beats the Earth at quite a margin. It actually reaches at some places the speed of Mach 3. Now what is Mach? The Mach is actually a dimensionless comparison of any ultrasound speed. If something is moving at a speed which is more than the velocity or the speed of the sound, and you compare the speed of sound with it, you can find out how much times it is greater than the speed of sound. So Mach 1 is the equal of sound speed, Mach 2 is twice that, and Mach 3 is thrice that. So when we consider Mach 3 speed, that means it is more than 3,000 kilometers per hour, and that is 2410 miles per hour. So you can find out that it is not easy to chase the shadow even in a normal plane. Supersonic travel is a rate of travel. I told you how to calculate Mach. Here I explain in this slide, and on the above of this slide you can get one reference. During 2017 eclipse, one application was made through which on the path you can click anywhere and can find out what was the velocity of the shadow or the speed of the shadow right at that point. It depends on the latitude, of course, so it changes from point to point. but the shadow is only 70 miles across and is moving faster than a Concorde. You can understand that its speed is almost 3 times the velocity of sound. So that is why it's too short, and that is why you can explain why the totality or annularity, exact annularity, is not really long lasting. And sometimes it is 2 minutes 40 seconds, sometimes it is close to 3 minutes, but it is rarely bigger than that. And this is the reason why it happens. So even at that speed, a military jet can probably match the shadow and follow it for some time, but not for a long time. But the highest record that we know of, in 1973, 8 astronomers, they actually was on board a Concorde, and they tried to follow the eclipse, and they did it. They did it for a maximum period of time of 74 minutes. But if we set ourselves to some vantage position, maybe in space, maybe in that Concorde, or maybe in some other space-bound vehicle, how should we have this spectacle? Will it be something different? Well, the simulation says that it will be something like this. Let us play this animation. Here you can find out, here comes the umbral shadow. Yes, at the line of demarcation where the day differs from night, and here it moves in this region. This is particularly the shadow that we are going to see this 21st June. So here it ends up in the Pacific Ocean. Let us play it once more. Here it comes the umbral shadow, penumbral shadow first, and then the umbral shadow. This is the path of annularity, and here it goes through Pakistan, comes to India, comes out, moves to China, then it bends down and goes towards the Pacific Ocean, and inside Pacific Ocean it meets the day end. Here is the evening, and that is why here is the end of the daylight, and we cannot any longer see it, and it goes beyond the Earth's surface by that time. So that is how we will have the spectacle. Now the third question is, we said that it is a rare solstice eclipse. We are actually very lucky to be alive right now, when we are experiencing a period where 5 solstice eclipses happen all in a row. But after that, there will be a long drought. We'll have a little explanation here. There was not one solstice eclipse in last 1963, and nor will there be one on the June of 2077. What is the catch here? The catch is this solstice, this eclipse will occur as the Earth's North Pole reaches its maximum tilt towards the Sun on 21st June 2020. Just 9 hours later, the Moon will pass perfectly between the Earth and the Sun. So the solstice point and this eclipse is happening within a separation of 9 hours only, and that creates an annular solar eclipse for a myriad to observe across Africa and Asia, and it is happening very close to the solstice. It's an incredibly rare occurrence. We'll explain why it is, but there's a good reason for this to happen this year. The solstice happens twice a year, we all know, and the Moon cycles through its full set of phases every 29.53 days, as Mr. Ganguly has already explained. In order to get a solar eclipse over and above these conditions, the Moon needs to be in its new phase, the phase that it only achieves when the Moon passes between the Earth and the Sun. We have already seen that. Now, getting a new moon to coincide with the solstice is not really so rare. About 3.4% of all solstices will have a new moon occurring within 12 hours of that moment of maximal tilt. 3.4% of them will come within 12 hours of the solstice point. Yes, that is true for any specific phase you care to examine. You can find out that 3.4% of solstices will coincide with first quarter moon, 3.4% of solstices will coincide with full moon, and 3.4% solstices will coincide with last quarter moon as well. Most recently, even Earth experienced a full moon occurring on 2016 June solstice. Before that, Earth experienced a full moon on the 2010 December solstice. But for the new moons, what about the new moons? We came very close to having a new moon on the solstice day in 2014 and 2006. But each time we were offset by approximately 24 hours instead of 12 hours. So it was a little late than that. You have to go the way back to 2001 to find out a new moon that coincided with the solstice, which it did once again on the June 21st of that year. And quite remarkably, that solstice new moon in 2001 also corresponded to a total solar eclipse. Very interestingly, 2001, another total solar eclipse on exactly the solstice day. That's a remarkable fact, and something that might come as a surprise. The solar eclipse occurring on the June solstice of this year, 2020, occurs precisely 19 years after the last solar eclipse on the solstice day, that is June 21, 2001. Now you might wonder that if there is a pattern so easy and the pattern at play that I can catch up, so it might occur to you that, well, go look forward and backward in time in 19-year jumps and you find exactly similar conditions. Well, sure enough, there was another solar eclipse on June 21, 1982. Yes, it happened. There will be another solar eclipse on June 21, 2039. That will also happen. And jumping ahead by another 19 years, there is still another solstice solar eclipse in our future on June 21, exactly 2058. So these 19-year gaps will be followed for quite some time. But this doesn't match with what normally we expect. A solstice solar eclipse every 19 years is too simple and too good to be true. It doesn't happen really like that. Because of very cryptic conditions that Mr. Ganguly has explained to a large extent, and I request all of you once again to go to my blog consciousignorance.com to have a more detailed study of it. But what we can say is this, that for every 19 years that pass, we experience almost 235 lunar months. 235 lunar months every 19 years. Exactly? No. We fall short by 72 minutes. When we do get an eclipse on the solstice, we tend to get a number of them in a row with this 19-year period. Once we get it, we get quite a number of them in a row at 19 years period. But then when enough of those 72-minute deficits add up, they push us out of sync with the solstice once again. So this is another cycle. This is called metonic cycle, in which we come in terms with it and then go out, and then come once again, have a series, and once again we go out of the series. And very interestingly, right now we are into one such series. Well, as I said, that when enough of these 72 minutes gaps, they add up, they push us out of sync with the solstices once again, and we go far off from the normally expected 19-year cycle. We are actually this time very lucky to live right now when we are experiencing a period where 5 solstice eclipses are happening all in a row. There was not one in the 1963, and nor will there be one on the June solstice in 2077. The eclipse cycles drift ever so slightly relative to our annual calendar over time, and this pulls events in and out of this 19-year pattern very slowly. We quite often miss it. We observe but don't process the observation. If you want to know when the last solstice solar eclipse occurred before this series, it was 1982. You have to extrapolate all the way back to December 22, 1870 before that. We had one solstice solar eclipse at 1982, but that was the limit of this series. Before that, we only had one at 1870 on December 22. If you want to know when the next one will be after the 2058 solstice solar eclipse, you need to jump forward all the way to the partial solar eclipse that will occur December 22, 2242, and there will be no solar eclipses on any solstice for almost 200 years once we pass the 2058 period. That is why it is something very interesting. Now let us go to another important observation. Well, normally when we look at the sky and we observe the eclipse, we find that the black spot, it goes in and goes out of the sun. Does it happen on a straight line? Is it that straightforward? Well, that actually depends upon where we are on the path. Very interestingly, this path will normally have a curved peak. These are curved paths, so there will be a peak, and very recently we were not within that peak, but this time in India we are in that peak. And since we are in that peak, we will find out that the sun is reaching its highest azimuth within the period of the eclipse, and so after that it will have a turnaround. The moon will have a turnaround and it will go to other directions altogether. Let us have some simulations, and before that, once again, let us find out the path really. The path starts in Africa, in Congo. We are considering the path of annularity, and then it goes through Ethiopia, Yemen, Oman. If you can follow my cursor, you can see. Then it enters Pakistan, getting over the Gulf, it gets into the Pakistan. And well, let me tell you one thing here, that this map is courtesy timeanddate.com, but the map of India that they have presented, we do not subscribe to that map at all. That map is wrong. So even though we use it, we do not subscribe to this map. We only want you to consider the detailed paths here, not the map of India. So what is happening is, see, this curved path is reaching its peak somewhere close to India, and here it goes to the peak. But here we have a considerable curvature, and we will see what happens here in this region when we observe the solar eclipse simulations this year. After that, it goes down and the curve flattens once again. If we are into this flat portion of the curve, normally we find that the moon comes in and goes out, rather following a straighter path. But when it comes to the conditions close to the peak, we will have a different spectacle. I'd like to point your attention and bring your attention to all that. Let us see what it happens. We start the beginning of our journey. I showed you, we start the beginning of our journey from this point at the beginning of the path of annularity. Then we will take different cities on the path of annularity at some interval. We will mention the country and the city name, and we will see how the solar eclipse would look like in those cities. Let us begin with Congo, and let us see when the eclipse begins here, the day just breaks in. So the sun comes in with a considerable part covered up, and then it happens the eclipse actually you are seeing in such a form that it is going out. Okay, now the next city on the same path. Here we are into the Central African Republic, a city called Obo, and let us see how the eclipse will look like here. Once again, the sun has to go up because it is very early morning, and then it covers to the annular form, and then you see from which angle it is going out. There is a slight deviation, but not much, more or less the same trajectory. Let us go forward to another city, and this time we are in Ethiopia, Lalibela, Ethiopia. Well, here when we look at it, the sun is already up and out, so let us wait for the eclipse to happen. Here comes the eclipse. Slowly we are getting in. We will go to the formation of annularity. Since we have taken only cities over the path of annularity, everywhere it will go to annularity, and then we will shift over. After completing the complete path, we will go over to other cities where it is also partial. So here also you can see more or less it is following the trajectory. Let us go forward a little more. Here we are in Oman, and see how it is. Yes, this first contact point, then it is going up. Here we will have the second contact. Let us see how it goes. Well, more or less the same path still now. Then more or less I said, still there are little deviations which are still not much discernible, but let us go forward and see how it goes. As and when we reach towards the peak, we are not yet at the peak, we are in Oman. So let us see how in Oman, Muscat, it is happening. This is the form. You can observe that the sun, the moon is already showing a little bit of deviation. We'll move forward to another city. Now we are into Pakistan, and let us see how it would be in Pakistan. Here is the point. When we began, the point of contact started here, but now it has shifted to this position, and we are approaching the annularity. After the annularity, it is coming out. It is coming out, but now its direction is something else. Well, now it is moving a bit to other direction. Let us see how it happens to another city which is farther down the line in Pakistan. This is Sukur in Pakistan. Let us see which way it goes. We are approaching the annularity. Almost reached. Here is the annular eclipse, but then since we are close to the peak, here the angle changes quite a bit. Right? It is actually because we are looking towards the other direction. Sun is going back from us, so naturally we have to look into other directions. And as we proceed to Dehradun, we are in India. Dehradun is a place, Dehradun and Sirsa are places where in India we can find ourselves on the path of annularity completely. So if we reach there, we can see the annular eclipse where it would be an obscuration of 98.84 to 98%, and in other parts beyond this line, see how much deviation we can observe here. And this is something peculiar this time to India, which normally doesn't fall, at least recently, it did not fall towards the close of the peak of the path, and that is why these effects are quite visible. Now we have gone past the peak and we are into China, but still a similar impact and similar effect is visible here. So the pattern, how it covers the sun and how it goes out, is changing depending upon the location from where we are actually looking at it. Though here everything has been made faster, that would happen very, very slowly. So you have to be really observant to find out such conditions. Now we have gone far away from the peak, though we are still in Tibet. Let us see how it is happening. I'm sorry, we are not far away. We are close to the peak in Tibet, and that is why it is a big deviation here. And let us move forward a little more so that we can make it faster. We can go down to well, this is towards the end of China, and see how it happens there. The first contact point has changed completely now. It is going to another direction, and it has also straightened quite a bit. Not much deviation, as we have reached a position far from the peak of the curve. And if we go even further, this is the final point almost, this southern tip of Guam Island, a little below the southern tip of Guam Island, and let us see how it will appear here. It will be more or less the same as we saw it in the last point. Well, if we go to other cities, we will have something interesting here. Even though the exact peak on the actual path, it is a path of annularity, it is not really reaching its peak within India. It is beyond India. But if we go into other shadow zones, we can find out that Kolkata falls on the peak in the penumbral region. So if you observe our Kolkata Center, Birla Industrial and Technological Museum will have a live telecast of that. So if you follow and observe that streaming, you can find out that here the phenomena of peak, the impact of the peak, you can see it here, because Kolkata in the penumbral region falls at the peak. And this happens because this curve is not exactly vertical to the equatorial line. It has a tilt, and that is why in Kolkata regions the penumbral shadow is actually peaking here. So let us go to that and see how will it appear in Kolkata. It is partial, but the deviation is quite spectacular and very easily perceived. Astronomers actually measure all such parameters and they find out the exact geometry of the dynamics that plays out between the celestial objects, in particularly the sun, moon and the earth. Here we are in Sirsa once again on the path of totality, and there you can find out, though it is not really exactly at the peak, but it is close to the peak, and hence the movement would be similar to that of Dehradun, and it is observable there. So these are the specialities. This is a very special occurrence when this path peak is falling within the zones of India, and that is happening this eclipse that we can observe. Well, these are the points that I wanted to share with you, that if you go through all such cases, you will find out that we will find these finer points. We can always share these fine observe these finer points and get to much more detail as and when we neatly observe any scientific or so I've stopped my presentation, and here it is. What I say is exactly this, that quite often we are not that observant, we miss the observations, we do not look deep into it. Our effort was just to show you that these are finer points and that will appear in this eclipse and many other eclipses, and if you follow, you can find out what is happening. It will be much more fun to know the science of it. Thank you very much, and thanks for joining us. Over to Mr. Ganguly.
Yeah, thank you sir, for your very good presentation. It was really informative, and I hope that people actually the viewers actually understood that this time the solstice point, that is solstice is quite means if you would like to, if I would like to add something to it, I'll just add it in a board, because it may appear something better. That for example, if we draw a celestial sphere, if we are here at a particular point, and if this is the horizon, and if you draw the celestial sphere completely, and for example, if you have our Calicut, which is at an altitude of 11 and 11.15 degree north. So if you have it here, we have the zenith here, and then if you have the celestial equator somewhat of that sort, this is the celestial equator, this is the extension of the terrestrial equator, and then if you have the our ecliptic, which is the projected image of the sun in the sky, if this is the eclipse, and if this goes like this, and if we have this particular thing like this, and our sun actually is the highest particular elevation. So this is actually the first point of Aries, and actually this goes on increasing, and this reaches highest at a point which is equal to, this is actually the obliquity, which is equal to 23 degrees 27 minutes, and along this particular ecliptic, as sun goes, this is the sun's ecliptic, so sun goes and reaches the maximum, this angle, when it reaches the maximum angle of, say, on 21st June, we have the summer solstice, it reaches the maximum angle, and when the sun is here on the ecliptic, if you take the diurnal motion of the sun, actually you see that the sun's path is somewhat of this sort, and it is somewhat of this sort. So we have the maximum duration above the horizon, and so it is the longest day in the year. And again, as the sun is moving, then it moves from that particular solstice point and it travels downward. So we have the motion of a curve, as the earth is moving around the sun, and the projected image of the sun on the ecliptic, and in this way actually we can see that the angle maximum we have in this particular time, on this particular solstice time, we have the maximum declination, and that is actually what sir was explaining about how this curvilinear motion occurs, and we are seeing on the surface of the on that particular map. So I hope all of you have actually enjoyed this particular presentation, and we hope to have clarified the concept of the eclipse as such, and the special aspect of this particular eclipse. I thank all of you for watching our presentation. Thank you very much.